We're now going to cover the factory method pattern. In addition to discussing the factory method pattern in general, we're also going to learn how to recognize how this pattern can be applied to enable the extensible creation of variabilities in our design and implementation. The purpose of this pattern is to enable the extensible creation of variabilities, such as commands, iterators, visitors, and so forth. This pattern helps to decouple the creation of objects from their subsequent use. Let's start off by talking about the context of applying this pattern in our expression tree processing app. There are many points of variability in our program. For example, we have different kinds of user commands. We have different kinds of traversal strategies. We have different visitor operations that can be applied on an expression tree. And we'd like to be able to add new instances of these variabilities without breaking existing code. The problem, of course, is if we tightly couple the creation of these variabilities with client code, then we're going to have a hard time trying to maintain the software without having to open it up, modify it, change the client code, recompile, relink, retest, and so on. For example, hard coding lexical dependencies on specific subclasses, such as evaluation visitor, print command, pre-order iterator, and so on, impedes extensibility and complicates maintenance. What are we going to do for the solution? We're going to abstract the creation of objects by defining a user command factory class that contains a method called makeUserCommand that knows how to make the appropriate user command object, or more specifically, the subclass of user command. There's a couple of different ways to do this. One way to do this is to define the user command factory base class and then subclass this to make different kinds of user commands. We could have a subclass called print command factory or format command factory, etc. We could handle it through subclassing, where the subclass would actually create the appropriate derived class of user command. Another approach is to pass a parameter to the makeUserCommand method and have it use this parameter to guide the creation of the appropriate user command subclass. For example, we could have the user command factory take a string, which would be the command to create, and then that implementation of makeUserCommand would make the appropriate subclass, print command, format command, eval command, and so on. Let's take a quick look at the user command factory class interface that we use to create the command corresponding to user input. As you can see here, we have a makeUserCommand method that takes a string and returns a user command. Naturally, that will be a subclass of user command, but from the client's point of view, it looks like a user command. We're doing it in a generic object-oriented way. The makeUserCommand method is the factory method, and this provides a nice decoupling of commonality and variability. The commonality, of course, is to provide a common interface used to create commands. The variability is to be able to have some way of changing which specific commands are actually created, based on, in this case, the string that's passed as input. There's a variety of different ways to implement the command factory. We're going to use an interesting approach that uses commands themselves to implement the command factory. And we'll look at this a little bit later when we talk about the implementation in more detail. But at a high level, here's the basic idea. Internally to the user command factory implementation, it has a hash map that maps the names of commands, format, eval, print, and so on, to a corresponding factory command object, which when executed will create the appropriate subclass of user command. So each factory command object basically implements an interface called iUserCommandFactoryCommand, and it creates a different type of concrete user command. We'll take a look at this a little bit later. It's a nice, clean way of being able to handle extensible factory operations by applying the command factory and the command pattern. The way in which we organize these various roles and responsibilities corresponds to a variant in the Gang of Four factory method pattern. The intent of this pattern is to provide an interface for creating an object, but leave the choice of the object's concrete type to something else, for example, a subclass. You should consider applying this particular pattern when a class can't anticipate the objects it must create, a class wants its subclasses to specify the objects it creates, or, in general, there's a need to decouple object creation from use. Here's a depiction of the structure and participants in this pattern. We have the abstract product, which is the actual object created by the factory. In our case, that's the base class user command. We also have a creator, which is the entity that's responsible for making the product or making the right product. In our case, that's the user command factory. We then have concrete products. In our case, that would be eval command, print command, macro command, set command, and so on. And then in the gang of 4 pattern, they talk about having a concrete creator that makes the appropriate type of subclass. We're not going to use that particular variant in this example, but be aware that it does exist in the pattern itself. Let's now take a look at and see how you could implement the factory method pattern using Java. We're going to define the user command factory class, and it's going to have a method called make user command. But before we show that, we're going to demonstrate how we set up the commands that are used to actually implement the factory. We define an interface called IUserCommandFactory command that has a single method defined in it called execute. And execute is going to take in a string, and it's going to return the user command. We then create a hash map, and the hash map is used to map command strings like format, print, and so on to the corresponding command object that knows how to create the corresponding command. We then go ahead and have our constructor initialize this hash map. As we're showing here, for example, we go ahead and put a new user command factory command implementation into the map under the name format. And as you can see, this anonymous inner class is essentially going to have an execute method that, when called, will return a new format command containing the parameters and the tree ops that it's going to be working on. So essentially, this is a factory command that creates a format command. It's kind of an interesting example of a double application of command using the command pattern as part of the factory method implementation to itself create a command. And we'll look at some other examples that aren't quite so recursive when we get into the implementation part in more detail. Here then is the actual make user command factory method itself. As you can see, what it does is it takes the input string and it parses it to figure out what the request is. Then it goes ahead and uses that command request to look up in the command map to see if it can find the corresponding pre-allocated command object. And if it finds it, it goes ahead and executes that command, which then returns the appropriate command. So we have commands creating commands. Kind of an interesting example of a double application of a pattern. If we don't find what we're looking for, we clearly were given an unsupported request by the user, so we just go ahead and quit. So let's go ahead and take a look, and we'll look at a couple of different uses of this particular model, this particular implementation technique for creating factory methods. We implement the factory method pattern in multiple places in our expression tree processing app. And it's one of my favorite patterns because it illustrates how we can implement one pattern in terms of other patterns. So let's take a look. Before we discuss the actual implementation of the factory method patterns, though, let's talk about some contexts in which these patterns are actually used, or this pattern is actually used. Here's the expression tree class. And as you can see, when the client application calls, the make iterator factory method turns around and uses the tree iterator factory make iterator to actually create the appropriate iterator, which turns out to be a strategy. So you can see all these interesting patterns being interwoven. Let's go take a look at tree iterator factory and see how we implement that. Here's the iterator factory class implementation. Take a look, you can see it's a public class, but it's got a really interesting implementation. Let's walk through this one step at a time. We used essentially the same approach for all the different factory method implementations that we show. We define ourselves an interface called Iterator factory command. And this is essentially an interface that has an execute method, so it implements the command pattern. And the execute method takes an expression tree and returns the corresponding iterator that we'd like to use. We then go ahead and make a hash map called traversal map that maps string names to the corresponding Iterator factory command instances. And if we take a look down in the iterator factory constructor, you'll see how this map is actually used. What we put in the map are strings that correspond to traversal order requests. So in order versus pre-order, level order, and so on. And for each of these strings, we go ahead and we make ourselves a new anonymous instance of the iterator factory command interface. So for example, for in order, we create a new iterator factory command whose execute method returns a new in order iterator tree. So it's making the appropriate in order iterator that corresponds to the strategy that we've requested when we invoke the factory method on iterator factory. And the same thing is happening throughout this constructor. For each different type of iterator strategy, we create a command object that knows how to make that operation when its execute method is called. Here's the actual make iterator method itself. This is what's actually called by the expression tree make iterator factory method. Make iterator takes in the traversal order request and does some default processing. If you don't give it anything, it defaults to in order. It then goes ahead and it looks up in the map to try to find the strategy that corresponds to that request. Assuming it does, it gets back a command object and it turns around and executes that command object. That command object will then return the appropriate strategy that we use to implement the iterator for that requested traversal order. If somebody tries to request something that we don't understand, of course, we basically throw an exception and bail out. So this is an example of how we implement the factory method for making iterator strategies. Let's go take a look at how we do it for visitors. Where do we create a visitor? Well, if you take a look at the state pattern implementation, you'll see a situation where we call the make visitor method on the visitor factory to either make a print visitor or an evaluation visitor. Let's go take a look at the visitor factory and we'll see how this is implemented. If you take a look at visitor factory, you'll see it works very much the way that our other factories do. We have a class called visitor factory. It defines an iVisitorFactory command interface with an execute method that returns the appropriate visitor. This is an example of the command pattern. We have a map called the visitor map that's used to map strings to iVisitorFactory command instances. The constructor of this class initializes the map for every string like eval or print. We make the corresponding anonymous object. It's a command object that knows how to execute itself and return the appropriate type of visitor. In this case, it would make an evaluation visitor versus a print visitor. And then if we take a look at the make visitor method, you can see the first thing it does is it comes in, takes the visitor request, which is a string, looks it up in the map, tries to find the command. If it finds the command, it goes ahead and executes it. Otherwise, it throws an exception. So that's the visitor factory. The last piece of the puzzle here we'll take a look at is the user command factory. User command factory is actually called within the input handler hierarchy. You can see here where the user command factory is initialized in the constructor for the input handler. And then if we go and take a look at something like verbose mode input handler, we'll see the use of the user command factory. So here's the make user command method. When this is called, it'll turn around and make the appropriate user command. So if we go over to the user command factory implementation, it works just like the other ones. It's a class, stashes away some things it needs. It stashes away a treeops instance, which is the expression tree that's the target of the commands. As before, we have an interface called iUserCommandFactoryCommand, which is used to implement the command pattern. Its execute method returns a user command. We have a command map that keeps track of the mapping between the command names and iUserCommandFactoryCommand objects. We store those in the map as follows. For each command, say format command or expr command or whatnot, we make the appropriate command object that knows how to make that kind of command. And then if we skip down to the very bottom, you'll see the factory method called makeUserCommand, which takes a string, and it has to do a little bit of processing just because of the way that the input is received from users, but it basically creates a command request and the parameter to the command, and then it looks up the command request in the map, and assuming it gets back a command object, it calls the execute method on that command object, passing in the parameters, and that's used to automatically create the corresponding user command. Naturally, if we don't get a command that we're looking for, we're going to create the quit command, which instructs the program to go ahead and shut down. So this is a nice example of how we implement factory method in our solution. We saw several different ways that it was done. There's actually even more of them I didn't show you. We'll talk about one of them later. But we used the command pattern to implement our factory methods to reduce the effort of extending and enhancing the various kinds of things that the factory methods create without having to write switch statements or if-else chains that have become difficult to maintain and understand over time. Now that we've looked at those various implementations of factory method in Java, let's talk about some of the consequences of applying this pattern. One of the benefits of factory method is it decouples several concerns. In particular, the client becomes more flexible because it doesn't specify the name of the concrete class, and it doesn't expose to the application the details of the creation process. For example, rather than writing a piece of code where we hard code a lexical dependency on print command, instead what we can do is we can use our user command factory and invoke the make user command factory method, passing in the string print. And internally to the make user command factory method, it will allocate the appropriate command in whatever means is deemed most appropriate given the implementation constraints and considerations. There's also some downsides to using this pattern, however. One of the downsides is we can end up with a number of additional classes that are required to handle the various cases, the various different types of commands or different kinds of entities we're trying to create. There's some implementation considerations to think about as well. We have to decide whether we want to use the pattern in a way that requires subclassing of the creator or makes that an option. The approach that's classically talked about in the context of the Gang of Four book is to have the creator class itself be abstract and it doesn't actually implement the factory methods, in which case, of course, it has to be subclassed. An alternative approach, which is what we're actually using here, which is also talked about in the book, is to have the creator class be a concrete class that provides a default implementation. Of course, it could be subclassed if you can't provide all the flexibility you want with the default implementation, but it doesn't become mandatory. And that's what we ended up using in our implementation here. If the factory method is passed a parameter to create variants, then you have to decide what type to pass. The most open-ended way to do this, of course, is to pass a string, but that ends up potentially not being type safe. Another approach is to pass some kind of enumerated parameter indicating which command the user requested. That's a bit more type safe, but it's also a bit more constraining. So you have to decide whether you're more interested in type safety, static type safety, or you want a bit more dynamism in your solution because perhaps you're going to be linking in various factories dynamically and you want to be able to make it open-ended how the clients interact with them, even if it's potentially the case that the clients ask for various kinds of products that are not supported at a given point in time. There's another implementation consideration as well. If you have a group of semantically consistent factory methods that all need to vary together, then you might want to consider applying another Gang of Four pattern called the abstract factory pattern. The intent of the abstract factory is to create families of related objects without specifying subclass names. This is a more complicated pattern. You would rarely apply this pattern unless there were groups of things that all had to vary together in some consistent and compatible way. You can think about abstract factory as essentially a group of factory methods that need to work together. The Gang of Four book gives some examples of why you might want to use the abstract factory pattern in the chapter where they present the Lexi editor for drawing and text. And they talk about wanting to be able to have different looks and feels supported by the Lexi program, where you might want to be able to come along and have one look and feel for one operating system or GUI environment versus another look and feel. And so you could use groups of factory methods, which are what abstract factories are, in order to ensure that semantic consistency. There's many known uses of factory method. It was very widely used in a lot of windowing toolkits, stretching back into the early days of frameworks and object orientation. More recently, it's also been used in various middleware. It shows up actually in a number of the Java JDK class libraries and various classes, things like the URL stream handler factory, which has a factory method for creating the appropriate stream protocol handler from a URL, and so on. So to summarize this pattern, factory method enables the extensible creation of variabilities such as commands, iterators, and visitors, and we use it extensively throughout the expression tree application to decouple the creation of objects from their subsequent use.